So, hi again everyone. I hope the lunch was good. Sorry you will not have a nap. We will restart directly. So now I will speak a little bit again of Virtio. I want to thank Stefano who introduced the subject. I will continue on this subject. So my name is Bertrand Marquis. I'm a principal software architect at ARM. I've worked for ARM for almost 5 years now, and I have also a background in safety, and I'm also a Xenon ARM maintainer together with Stefano, Julien, and Miral. So, together, today, sorry, nap time, so please excuse me. So we will speak a little bit about Virtio and an initiative that was started around a year ago, sometime after the last Xen Summit, because some new problematics are arising or some problematics already existing now need a much better solution. Okay, so I will do a quick summary on what is Virtio. Well, that was planned in my presentation. I'm not quite sure this is needed anymore, but still. And then I will explain you why do we think that we need a new Virtio transport. I will explain you a little bit about the design that we currently have on application over FFA. FFA is the firmware framework for ARM-A profile. How this can be applied or used on Xen, and then quickly present you the current status and the future work, because we need your contribution. Okay, so what is Virtio? So first, Virtio is a standardized interface to access host or distant VM devices. That's a specification currently at its version 1.3, which is maintained by the Oasis Foundation. The goal of Virtio is to solve one issue. We don't want to have one driver per platform and per application. So we want to have standardized drivers that we can reuse on all platforms and mainly on most hypervisors and virtualized platforms. So there are three main components in Virtio. The first one is a standardized driver. So you have one Virtio defined design for each kind of standardly used driver, so Ethernet, blocks, SCSI, and I will fall, console, etc., and so on and so forth. And some new ones are added along the way. GPU is heavily worked on at the moment, and some new interfaces are popping up for automotive markets like Kind, I2C, SPI, you name it. Down from those drivers, the Virtio specification is defining the notion of transport. This is how those devices are discussing with the other side of the Virtio, which is emulating those devices. So currently in the Virtio specification, there is transport on MMIO, register-based, PCI. Well, everybody knows what PCI is. And there is a third one, which was introduced quite some years ago by IBM, which is specific to the S390 platforms, because they had a specific bus to discuss with devices. And the third component of the Virtio specification are the virtual queues. Basically, the virtual queues are defining how you communicate between a device and a driver through DMA, so through memory. So there are two main use cases currently of Virtio. First one is VM-to-VM communication. You have a VM giving you a disk, having access to a disk, and you want to provide another VM to access part of this disk. And the second one is emulators. So for example, Qemu can emulate devices using the Virtio standard so that potentially any OS supporting Virtio can run on Qemu without needing to write new device drivers. So currently Virtio is supported in most open source OSs and hypervisors, so Linux, Xen, KVM, and it's also more and more supported by proprietary operating system, mainly in the embedded workspace, because it costs too much to rewrite your proprietary OS for all platforms. So if you say that you use Virtio, you can virtualize the proprietary OS without needing to port it to each and every platform. So how does Virtio work in Xen? So there are three components. The third one, I will not speak too much of it, but first one is Virtio MMIO. So Virtio MMIO, as I said, that was based on registers access. You cannot make register access from one VM to another. So how is it working? It's working through something named IOREC, where Xen is catching up the fact that a VM is accessing a register, which it has no access to. And Xen is forwarding the request to a VM where there is a Virtio backend. The VM is telling to Xen, oh, register X has been accessed. You need to answer whatever value to the VM who did the access. So from the VM point of view, when this is done, this is completely transparent. Whether this is a VM emulating the IO access or this is a real register being accessed, that's exactly the same thing. Okay, this is important for the next thing. The second thing that we have in Xen, thanks to Ian, is Virtio grant. So Virtio grants, the problematic we try to answer with that is, I have a guest and the backend needs to access part of the guest memory. So we go through the grant tables to actually grant access to part of the guest memory to the backend. This is solving the problem of making the assumption that my backend has full access to the whole memory of the system. So you have less memory being accessed by the backend. So this is done through a kind of a new Virtio device transport, not completely, and it was made to be used mainly for PCI on x86, but it's also usable on ARM using Virtio MMIO. It's really Xen specific. Okay, you have something that is only working on Xen on this. Then there was the Argo initiatives. That was the idea of Argo was we will try to make everything secure by saying you don't grant access to anything, and the hypervisor is basically doing copy from memory to from one VM to another VM. There is not a lot of progress on Argo at this time, so the main solution used at the moment are Virtio grants through Virtio PCI or Virtio MMIO. Okay, so that's the current status. Lately, there are new use cases arising for Virtio. So, okay, not working. Is it? Ah, yeah. So, the main use case we know is the VM-to-VM communication. So you have a device emulated by a VM, and you have another VM who has a driver and accessing this device. That's the original use case. Now we have two new use cases which are arising lately. The first one is the system-to-system communication. So same thing, you have a VM with a driver, but the backend is emulated in another system. So I'm using the name system here because there are lots of different use cases of this. So there is the easiest one, that's two independent core that you run in an AMP configuration. Then there is a use case from Stefano, two independent systems cross-connected by a mailbox which have partial memory access. And some other have the idea of, I don't have a mailbox here, but I have network here. This is a use case arising just because they want to make this VM completely independent of the fact that the backend is here, or on ARM is here. And this is the third use case. That's on ARM. So for people knowing the ARM architecture, we have something named trust zone, where you have two parts in the CPU, the normal world and the secure world, which are isolated by the hardware. And they want to have the Virtio device emulated in the secure world so that the normal world can access it through Virtio means. So mainly, the use case here is to have a network device emulated on this side, accessed by the other side. But they want to do that with Virtio so that, depending on the system design, you could put that here, or you could move it here if you don't have trust zone on your platform. They want to have something completely generic so that this part, which is usually the expensive part, is not modified. Okay? So in the secure world, main use case is to have OM or SIP services provided, which means that your platform is coming with a firmware. The firmware has some services. The services are provided as binary running in a secure world. And whatever you put in here, you don't care. That's using Virtio, so you don't need to change it. So you don't need, the OM or SIP does not need to create SIP drivers in the operating system, which is kind of the ideal solution for board manufacturers. It means that They don't have to provide you any driver for Linux, QNX, WinRiver, Windows, you name it. Okay, so this is why we wanted to create a new transport. So, what are the problems with the existing transport that we want to solve? Well, in the VM2VM case, that's the trap and emulate. So trap and emulate is the use case that I explained before. The VM is doing an access to a register. It's cached because nothing is mapped at this address. We decode what was being accessed, and we push the request to a VM, which is telling us what to answer to this memory or register access. Problem from the trap and emulate is first you have lots of context switches. Every time you access a register from a VM, you switch back to the hypervisor, you switch to a VM, the VM is doing some processing, you go back to the hypervisor, and then you reactivate this VM. That has a cost in performance, and it creates a problem in scheduling, because from a VM point of view, a register access is atomic, right? You are doing one read operation, you read, you get the access back. But with our hypervisor, now we need to freeze the vCPU until the other VM actually gave an answer. And if the other VM cannot be scheduled straight away, you have a potential issue in the requester, which will detect that there is a deadlock in the core. So there are scheduling challenges. Now, in the system-to-system, we have exactly the same issue. We need to trap in the hypervisor, then we need to create kind of a protocol, send a message to another system, the other system will process it, and then later, it will provide us an answer. So we have exactly the same scheduling challenges, and we need to create, once again, a new protocol to communicate between those two systems. Then we have another issue, that's the assumption that the backend has full access to memory. If you remember earlier, that's what we tried to solve with the Virtio grant solution. But what if those two systems are running differently? So you have system to system and not all the memory is accessible. What if your backend is running in trust zone in the secure world? You cannot say that trust zone will access the full normal world. This is going against, for example, the safety concept. You cannot grant access to everything because then you create problem for everything. So we have a DMA problem that we want to try to solve. And final point is the current transports existing, you see it by their name, they have been designed for hardware emulation. So basically for the Qemu use case. You have PCI or MMIO, that's an existing hardware bus. So you need to emulate this bus on PCI. You need to emulate the full protocol to generate a PCI backend. On MMIO, you have the trap and emulate. Well, you have the same thing on PCI, but on PCI, you have also the PCI bus to emulate. Channel I/O, very specific to an architecture, not applicable. So it's not adapted to our new use case, and it's not optimal for the currently existing use cases. So for that reason, we started to work on how can we solve this. So we decided to go through messages. Why is that? Well, a message, you can transmit it through an IPC, through an hypercall. That's better than doing a register access because in a message you can transfer more data in one go. That's one hypercall for how much data you want instead of one register access. Well, you could implement a message-based communication with shared memory and signaling. That's also working in the, for example, the trust zone use case. You can use a mailbox. Well, if there is enough space in your mailbox, otherwise you have other solutions using also shared memory. And on ARM, you can use FFA. So the firmware framework for the A profile, I will explain later, has the required functionality so that you can send a message from a VM to a VM or from a VM to the secure world. Second point, a message can be handled asynchronously. The scheduling issue that we had was due to the fact that the hypervisor had to freeze the VM until we were able to provide an answer. Now, if we send a message, the VM can know that it needs to wait for the answer, so it can do something else in the time between. It's not blocked anymore. So we have no busy wait compared to the trap and emulate. We can do parallel handling of different devices, so you can communicate with several VMs. And in some cases, synchronous is also possible. Right? In the secure world example, when you communicate with the secure world, you do a context switch to the secure world and then you come back. So synchronous messages could work well in some cases, depending on the design. So it felt like it was adapted to our use case, VM to VM, VM to secure partition, and system to system. So how did we design that? So first, the main goal is to have something that we can name a standard. So we want to have this in the Virtio specification. So staying on a part of MMIO PCI, we will try to add a new standard which will be named, well, name might change. So we are not that strong on the name, but we will put out a new transport which will be message-based. So the transport will define a small set of messages, so that's the features required by any transport in Virtio. Setting device features, configuring the device, changing the device of the status of the device, or getting the status of the device, resetting it. And final one, the virtual queue configuration. So that's the minimal set of messages that we can do, and we can optimize so that we send less messages than in the trap and emulate use case. So basically, the transport will just convert the driver request to messages, send them to the other side, and get back an answer, and give back the answer to the driver. And we can handle the non-blocking weight in the transport. The main goal is not to change any of this, keep them standard. So we need to make something that is completely transparent for the existing driver, because we want to benefit from Virtio. We want to reuse the existing Virtio. Final thing is we need interrupts or signaling. So for that, we will also use messages. Why is that? It's more generic, and in a message you can transfer data. And in some use cases of Virtio, there are data that are required together with interrupts. That's in the virtual queue, the index of virtual queue, the offset when something changes in the virtual queue. And in device configuration, it could prevent to re-look at all the configuration if, together with the signal from the device, you could also get what configuration has changed. So that's the transport part. And down from the transport, we define something named a bus. So why a bus? It's because it's looking a lot like the PCI or MMIO things. You have a transport, and then you have a bus implementation. The idea is to make it possible to implement a bus over several channels. So here I made an example using Zen, an example using FFA, or an example using a mailbox. The idea is to split the implementation so that the bus implementation is as simple as possible, because basically it needs to send and receive messages. That's the only requirements we have. And then the bus will be a bus because it will have the same semantics as the PCI or MMIO bus. Means you will have a bus and device discoveries. So could be through device tree, could be through an enumeration process. The bus could have a specific DMA handling. So basically, for each device detected, the bus can define what are the DMA operations. So we can have the bus handling the memory sharing or unsharing required if the bus needs it. It needs to transmit and receive messages, and at the end, it has very simple and limited functions. Okay, so we divided the concept in two to make it possible to have several implementations. So first example is over FFA. Why is it the first example? That's because that's the first example we started from because we have it. So FFA is really suitable for that because FFA can transmit messages. You have direct messages, that's synchronous messages, so that's adapted to VM to secure world communication. And we have indirect messages, which are asynchronous, which are well adapted to VM, in some cases VM to secure partition. There are system design where the secure world is asynchronously scheduled. And the indirect messages are working well for signaling, because that's a send and forget design in FFA. We have solution for DMA handling, because in the FFA specification, there are means to share and unshare memory, or even to lend memory to someone else. So we could do ballooning, for example, with that. And then FFA has what is required for bus discovery, because you have a UUID-based discovery. So the idea would be that a bus is identified by a UUID, and then we design new messages so that you could detect what devices are available on a bus. Okay. The big advantage seen in the market by the FFA implementation is that it's becoming hypervisor agnostic. The only requirement for the hypervisor here is to support FFA. If you have FFA support to transmit messages, do memory sharing, and have UUID discovery, which is what I'm working on in Xen, you don't need anything specific in the hypervisor to do Virtio between VMs and between VM and the secure world. So we could remove completely anything related to Virtio from Xen if we do that. But there are other solutions. What could be the solution for Xen? There are two, in fact. There is the FFA one. Advantage is, well, you don't need something in Linux. If there is an Virtio over FFA, you have it by default. Same thing on the front end and the back end. In the hypervisor, you only need the FFA implementation required by Virtio, not more. So advantage is no Virtio specific code for Xen and support for any type of guest. So proprietary OS just need to support FFA to have it working. Limits, it's AMP specific, definitely, and there is a tool aspect, which we will start to check. But there is a second solution for Xen. It's to implement a Xen-specific bus, which could rely on ground table and a combination of Xen store and probably some initial memory sharing to exchange the messages. And probably events to signal on the other side that a new message is available. Has to be designed, but definitely that's something possible to do and should be fairly easy. Advantages for Xen is on the backend side of things. If you have the bus implemented in the Linux kernel, you don't need to do any Qemu or emulation implementation anymore. We will remove the IO-rec requirement that we have right now. Will not be architecture specific. We could optimize the performance that compared to FFA potentially. Not sure, but that's a possibility. Main advantage is it's architecture agnostic. The only limit is we will have to do the bus driver implementation per operating system. But it's fairly limited to something transmitting and receiving messages. So what is the status? Right now, we have a draft design or a draft specification. We have a first proof of concept implementation ongoing. So it's done by Google between Trusty and their Trusty Trust Zone implementation. And it will be done by Google between Linux and their Trust Zone implementation. So initially, the work started with Google, ARM, and Linaro involved. But now that we have a proposal and we have several interests in the industry, Qualcomm, ST, and other company, AMD apparently is interested also. We will create probably a community group in Linaro that will work on the specification and the first implementation in Linux. And people from the OpenAMP Virtio group in Linaro will probably join also this group. What are the next steps? So the first step is to write the transport in Virtio specification terms. That's what we will do in the next year, and publish it to the Virtio, to Oasis, so that it's added to the Virtio standard. And the implementation in open source project. So Google and Linaro will work on the Trusty Android implementation and Linux. I will work with Linaro on the FFA implementation. And we are still to define who will work on the Qemu backend implementation, a mailbox, bus implementation, or Xen implementation in the future. And definitely, we need contributors. So if you are interested, even if it's only to come to the meeting and stay there doing nothing, please tell me, and you are more than welcome to come. Thank you very much. You can take back your phones if you have any. Do you have any questions? Yes?
So this new Virtio transport mechanism or protocol sounds a lot like channel IO. Basically
It does.
The same, just under another name.
Yeah, we investigated the possibility to reuse the channel IO and to make it more generic. But there are some flaws in the channel IO that it's kind of useless to try to solve.
Similar to the relationship in PCIO
And MMIO.
MMIO.
Yes.
Channel I/O.
There are some messages that we might reuse. There are some others that we won't. Channel I/O was designed to really fit to the S390 bus implementation, which is creating some flows where, for example, they have to divide some messages in several because they don't have enough space. They can only transmit one message at a time. We don't want to break that. But we can learn from that and make that better when possible. And that's why I'm discussing with Bill Mills at Linaro, for example, who knows well this kind of problematics, so that we can optimize the protocol to reduce the number of context switches compared to the channel I/O. And the channel I/O has a big flaw for us. It takes into account that the backend has full access to the memory. So we would have to rewrite the driver and change it completely to have a device discovery system and have DMA, which here can be directly included in the bus implementation, if wanted. Not, it's optional. Yeah? Any other question? Yeah?
A question on how migration will work with Virtio message, because I imagine that in theory you could move your VM and your backend would stay running on the source, and when you're ready, you can transparently move it without the VM having to renegotiate anything. Is it possible to do such kind of transparent migration?
In theory, yes. Basically, it's your backend, if not moving, your bus can still be detected from another VM and you will redetect the same devices. Now, in the case of VM migration, the point is you don't want to break ongoing communications. So you will need an extra protocol. This question, you're not the first one to ask it. There is a general question to ask on how can this work for Virtio? Where do you freeze Virtues and transmission and so on and so forth? But definitely that's a subject to look at. We have the same problem, which has been, another problem like that which has been raised, that's the question of the backend coming after the front end and the current workaround done by AMD where you put a status bits and etc. Right now, that's some question for which we need more contributors to know what is the best solution to solve this use case. Definitely, this is one that would be interesting to discuss. Yes?
Could this be used in Argo?
No. Well, yes. You could define a message transmission which would work by copying the hypervisor. But it would be kind of pointless to use the Virtio message transport on top of Argo. You have a better means to do that. The point of Argo is not to solve the configuration and register issues. The point of Argo is to say you don't share memory, so you do memory copy inside the hypervisor. So in a sense, yes. In another sense, no. Sorry. There is no straight answer to that one. Any other question? I think we are at the end of time. Well, at the end of my time. Hopefully not the end of time. Yeah? Okay, thank you everyone.